喂 hello yes it's not showing 按这个投影片开关。I need to be careful about the volume. Let me turn it down first. 好，这样应该还 OK 吧？有点it's clear enough. All right. Okay, so welcome back to DSP, and this is our last week of lectures. Thank you for apologize for the delay. So I was stuck in a meeting. It was a admission meeting. Admission, yeah. 招生放榜啊。Tomorrow will be the announcement of college application. 个人申请二阶放榜啊。So there, the university always has a meeting like that to make sure that everything is correct. So all the department chairs have to sign the form to make sure that all the names and all the order, 放榜名次的 rank is correctly printed. So we'll do that tomorrow. Okay, so yeah. So that's why that's an important meeting. So there was a delay. I apologize for that. But then, because of delay, I decided that this last lecture is not going to be included in next week's final, just to make our life easy. But it's fun stuff. Yeah, it's interesting stuff. I just want to ensure that if you wait for me, you got the freedom to decide that maybe your time is precious. You can go elsewhere. You can skip this lecture. That's fine. But in the meanwhile, this lecture will be very much about your homework number 5. In homework number 5, there's the computer part, right? So I uploaded a file which contains telephone tones, and I asked you what numbers they are, or what is the phone number, right? In case you haven't taken a look. So that's homework number 5, the computer part. You're asked to answer what's the phone number. Right? Whenever you dial a phone, you hear beep, 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 the beeping sound, right? So actually the sound will be part of our topic today. So today's topic is an introduction to what I call spectral estimation. We estimate something, a few things from a spectrum, and that is called spectral estimation in the frequency domain. Estimation in the frequency domain, using what? Using short-time Fourier transform, okay? So as a part of motivation, this is a telephone pad, and there's an array of 4x4. Usually we don't see these anymore, okay? I haven't seen the last column at all in my life, but this is an image I downloaded from the web. So which explains that actually the idea is very simple. Each time you press on a button, 2 tones, tone 就是那个纯音啦，就是 a sound with single frequency. That's called a tone. You hear a combination of two tones. It's fairly easy. So each row here, 1, 2, 3, that's the first row, second row, third row, last row, corresponds. Each row corresponds to one of the four frequencies. And each column, similarly, each column, usually we have 3 columns nowadays. Just you can forget about the last column, but the standard was made over there. So theoretically, you could also use the 4th column. But for the 3 columns we typically see on the phone, each column corresponds to one frequency. So, for example, you press on number 5. You should hear what you are going to be hearing is a combination of 770 hertz and 1336, 2 frequencies. Easy enough? So just to give you an idea, so I prepared a few files. So for example, 770 sounds like this. That's 770, okay? And 1336 is like that. So can you now, I ask you to imagine what does it sound like when you put the 2 tones together? Can you imagine in your head? For those of you that are more musically inclined, 如果对音乐比较有感觉的话, you're more musically inclined, can you imagine hearing these 2 at the same time? And that, can you imagine that? You will have some sort of interval, okay? So when you play them together, indeed, that's number 5. Number 5 is this. So it's a very simple idea, okay? That's how technology advanced in the past. The phone pad, each button corresponds to a combination of 2 tones. We use the frequencies to encode which button has been pressed. Okay? So far so good? So it's fairly easy in case you're interested. Seriously, I use this a few lines to create the combination tone. So I have Y1 A sine frequency 1 of T. Y2 equals to A sine frequency 2 of T, T being a few seconds. 1 second actually. 1 second. Duration is 1 second. So 1 times the sampling frequency that equals to 8,000 samples. So time goes from 0 to 7999, right? Exactly 1 second. So in this, you can just easily create a dual tone and that's the result you're hearing. Okay. Fairly simple. So a bit of history. Have you ever wondered why the buttons need to make sounds? If I ask you, it's an open-ended question. Have you ever wondered? Have you ever wondered in your life? 侦探里面有演那在他演之前，你有 ever wondered? Has anybody? Yeah. 什么帮什么？视觉障碍。That's a good point. So you mean that if you're visually impaired, you should be able to just press the button and make sure by listening to the sound. That's a good point. What other have you ever wondered why do buttons need to make sound? What if they don't make sound? It's just a button on and off, right? Why not? I think my answer is that you remember the telephone line is an analog system to begin with, in early days. So all the infrastructure analog communication, okay? So in the past, it used to be like you talk to the phone, your voice is analog. And everything is transmitted through the landline in analog fashion. So in the old time, if you need to encode the number, and you cannot do it digitally, how would you do that, okay? You might need to convert everything into sound first, because voice is sound. This entire system, the entire transmission system is designed for transmitting sounds. Okay, so that's why you also need to encode the button as a combination of some kind of sound. And the easiest way they figure out is a combination of 2 tones. Okay, so that's my part of the answer. For the visually impaired, I think it could be interesting. Maybe we can all learn to hear the sound and be able to tell the phone number. That'll be a special talent. Okay, 可以在电机之夜表演And You know what this is, right? You're not that young. Have you ever called on public phone like that? You need to insert coin. You have the idea? Do you have any idea? You're not that young. 你会投币这样的？电话卡啊，电话卡已经是比较后来的，更早都是投币啊，更早都是投币。And you can imagine that if you call international call, early days, 1980s, if you make a phone call to the U.S. through the public phone, you prepare like $100 coins. And you keep inserting every 3 seconds. I'm serious. Don't laugh. That's what happened all time. When you make a phone call to your friend in America using this, you go to the bank first and ask for a bag of $1 coins. Or you can insert $10 each time. So you just keep. That's the old time. Okay. Public phone buttons. There was one. Almost 10 years ago, we still have one of the phones on campus. Okay. So the system. So that's a bit of history. And I have a story to tell. Actually, when I was in high school, my friend used to have a watch like that, a smart watch. Back then, Casio, made by Casio, the Japanese brand. Their buttons, right? And the watch can make sound. So somehow my friends showed me that they were able to hack this system. You can pick up the phone and then play a sequence of two-tone combinations to the receiver, and somehow in that way you can bypass the need to pay. It used to work sometime around 1990, but later, very soon, the government found out this is a漏洞, so they fixed this problem. So after that, we could not do that anymore. So seriously, the phone number is encoded and transmitted using sound, using a combination of two tones, okay, in an analog system. Okay, so in this lecture, I would like to cover in more detail this classic dual-tone multiple frequency technology. That's the name, dual-tone multiple frequency technology. And imagine that now if you are somewhere in the path of transmission and you need to decode the phone number in order to route the communication, routing, right? Yeah, because your phone call is meant to be delivered to somebody who owns that number, right? So as far as routing, 就是路径要怎么排 is concerned, everywhere along the path there's need to decode the sound back into phone number. Okay? So imagine you need to do that, and that's your homework. Okay? So I suggest that this can easily be done by DSP. We will use short-time Fourier transform, and chances are you by correct choice of window, and by being careful about the resolution, frequency and time domain resolution. We began that topic last week. So by careful choices, you will be able to decode the phone number while receiving the tones. Okay, and then there are two. I don't know if I have time today to cover into details, but this is a borrowed lecture from my graduate level course. I have a graduate level course called Audio Signal Processing, basically. So this is one of the lectures right there. So in that lecture, and this is a copy from that lecture, so we have an issue of two very similar ideas, resolution versus accuracy. In Chinese, resolution 可能可以翻译成什么解析度啊 right? But accuracy, I claim, is has a slightly different notion. 那个意思不太一样。Accuracy 是准确度， but resolution 是解析度啊。So your estimation can have a high resolution, can be based on high resolution representation, but it lacks accuracy. Can be really wrong with high resolution. So the two terms have different notions. And they deal with the main problem is interference versus noise contamination. Every recording has noise. That's a point that we haven't really been talking about throughout the semester. Every recording of any kind of signal has noise, right? So when your signal is contaminated by noise, how could you ensure you estimate, let's say, the frequency? 770 is the frequency. You estimate the frequency accurately. So that's a concern, okay? So noise is always a concern, and it affects accuracy. So we have a part like that. And then it turns out that this is really, really advanced. Okay, so Fisher information and Cramer bound. I think I'll skip it for today. All right, so the first thing, let's begin. Spectral estimation. And we talk about decoding the dual tones. Okay, so you have for the number 5 a combination of 2 frequencies. And this is a plot in the frequency domain, in the time domain. That's a waveform. That's a waveform of adding a 770 Hertz tone with 1336, a combination of 2 tones in the time domain. Okay, and the time now we're looking at about 20 or 30 milliseconds. Making sense? Does it make sense? This is what happens in the time domain. All right, so how do we estimate the signals, the frequencies? If you just look at the time domain, it might be tricky. Yeah, I told you this is number 5, so you know the answer is that, right? But can we agree that in the time domain it's quite tricky to figure out what the 2 frequencies are? I don't have a really good answer to that. Okay, maybe you can do it in the time domain, but this is what we're going to suggest. Okay, we do it in the frequency domain or in the time frequency plane. Right. So let me explain. So first, we would take the input and discretize it into digital format, and then we apply a window. We apply a window, so the window has a length. And then we use what we learned last week, the fast Fourier transform, to go to the frequency domain computationally. Okay? The multiplier input with the window, let's say, if, for example, if this is a window, you can imagine multiplying this bell-shaped window, which must be a Han window, with your signal, you get a packet of some sort. Okay, you get a wave packet that's focused around this time, centered around this time, and the window length is nicely set at about 20 milliseconds in this example. So you multiply your window with your input, and then you expect, then the question is, what do we expect in the frequency domain? Suppose we can assume that there is a combination of 2 tones, and the only unknown is the frequencies. Suppose that we can just safely assume that there are 2 tones, it's just the frequencies we don't know, right? If you can make that assumption, how do we estimate which 2 frequencies are they? How do we do that? What do we expect to happen when we multiply that unknown signal with a window and then go to frequency domain? What do we expect to see? What do we expect to see? And that's your homework. That's homework number 5. Okay, what do we expect to see? So if you can see something, then maybe you'll be able to figure out which button is pushed. Okay, now which button is pushed? So a bit of math, all right? It's actually not that hard. So suppose that we've already assumed, this is by assumption, if Xn really is a combination, a linear combination of 2 tones. Suppose that's true. Okay, suppose that's true. Suppose what's being transmitted on the phone line before the voice communication started, there must be nothing but the phone number, right? The voice hasn't come in yet, right? So suppose that we really can assume the signal is a combination of 2 tones with amplitude A1, A2, also unknown, and cosine phase unknown, phi1, phi2. Frequencies are also unknown, F1, F2 in hertz, where this T, big T, is the sampling period. Big T is the sampling period. So far, so good. Can we agree that this is a very general form for a combination of 2 tones, 2 pure tones? That's what a tone means. A tone means cosine a amplitude cosine of one frequency, maybe a phase shift. Okay, unknown turns out to be unimportant phase shift. No, phase 不是很重要啊。Phase is not important. So far, so good. Can we agree that this is a linear combination of two tones? Then let's jump to a conclusion first. We expect that if this is really xn, then its Fourier transform we know. We already know that by now you should be familiar that the Fourier transform should be the spectrum of x. Okay. Again, I'm using a sloppy notation. X. Let's say if this big X denotes the spectrum, the Fourier transform, the DTFT, then we know that the DTFT should be amplitude times divided by 2 plus times EJ phi 1. Okay, and the intermediate state is because cosine is a real part of cosine is a real part, right? The real part must be itself equals to itself divided by 2, right? Plus divided by 2 plus their complex conjugates, which I haven't written. I didn't bother to write it down right there. This is just changing cosine into 1 over 2 EJ something. Okay, you all know how that goes, right? So therefore, the Fourier transform, if you just go directly, by the way, we haven't applied the window yet. This is just assume that the button has been pushed down forever. Okay, let's assume that somebody pushed the button and forever. Okay, for the ideal case, that's what it means. We have a signal in time which is there forever. Okay, for now. So then, since it's pressed down forever, the Fourier transform is delta function, right? It's a combination of delta function located at omega 1 and omega 2, respectively, plus their negative frequency components. There's another one in negative frequency range. Okay, so I'm missing a few things. So here, apparently omega 1 equals to what? Omega 1 equals to 2 pi f1 t, or it equals to 2 pi f1 divided by fs. If that looks more familiar. And similarly, omega 2 equals to 2 pi f2 divided by sampling frequency. Okay. So far so good. So this is just good. You know that the pure tone corresponds to delta function. Okay, and that's an important concept. You have a pure tone in time, right? You have a pure tone in time with frequency of f0 equals to 1 over something. 1 over its period. Single tone, so that when we go to the frequency domain using DTFT, you expect the answer should be, there's one component right here, another component right there in the omega domain, right? Where you should expect in omega 0 and minus omega 0, okay? Or let me just say 1, okay? T1, so 1, 1. So that's what you will see in the frequency domain, this being x in the time domain, this being big X. Usually we write EJ omega, okay, throughout the semester, but I'm being sloppy. 我这边是用一个比较简洁的 notation. I hope you don't mind without confusion, okay? So far so good. So that's the important first thing to notice. Realize that a tone is very simple in the frequency domain. Cosine is so simple in the frequency domain, just delta function, okay? One right here, one right there. That's a combination. That's one tone. That's one tone. One tone equals to one component right here, one component right there. Okay. So if you understand that, then we are ready to apply the convolution theorem, okay, of the second kind. Okay. So that's the next page. So how about now short time Fourier transform? This is good old DTFT, not yet short time Fourier transform, just DTFT. So then you can ask, how about the short time Fourier transform after windowing? Okay, how does this relate to the spectrum, okay, the DTFT. How does the short-time Fourier transform now as a function of both frequency and time shift? How does that relate to this this simple fact? So next part, now we know that x is just written as cosine, right? Cosine is one component right here plus their complex conjugate. CC stands for complex conjugate. Okay, let me write it down. CC 是 complex conjugate， 共二复数的部分啊 ，complex conjugate。Now, when we multiply our signal with the window, and then take the Fourier transform, this is what we get. We get the Fourier transform of the window, but shifted to that frequency. So remember Fourier transform of the window, okay? Rectangular window, Hahn window, Hamming window, or if you will, Kaiser window. Why not? Yeah. And this is a shift theorem, okay? Because our signal is a pure tone, so in kind of communication jargons, in communication terminology, you can imagine that this is a carrier, and this is a message. Okay, so this is a baseband. The window is long, and now we have a carrier of a frequency which shifts the spectrum to where its frequency is. This is shift theorem. When we multiply x with w, then take the Fourier transform, we are modulating w, the spectrum of w, to that frequency with the adjustment for the magnitude and phase. Is this clear? Is it making sense? Does it make sense? And similarly, because of the presence of the second tone, we are also modulating the spectrum, or shifting the spectrum of the window to this other location. Okay, we shift big W to the right and to the right, and also to the left, because there are the negative frequency components. Okay, so in the end, so we can compare the DTFT and the spectrum with windowing. The only difference is that we expect to see a spike, delta function at omega 1 and omega 2. But similarly, we expect to see not a spike, but now a copy of the Fourier transform of the window, also centered at omega 1 and omega 2, centered. 它的中心点在那边。Yeah. So that's our idea. That's what's going to happen when we apply a window to multiply our signal. And we know that our signal is a combination of two tones. Okay? Combination of two tones. I hope this is making sense to you. Okay? So that is to say, if our signal xn is A1 E J omega 1 n. If that's our signal, and then we multiply our signal with a window function, okay, with a window function, then the first transform of x with a window, if you take the first transform, you expect to see the spectrum, a spectrum which also has two components. One is located centered around omega 1, and the other one is a negative frequency part. And you expect to see a copy of the Fourier transform of W. So let's say this is the Fourier transform of, this is the magnitude, okay? So you expect to see a main lobe and side lobes. That's probably one thing I really want to point out. Okay? You expect to see the main lobe of your window function, as well as side lobes. There is going to be some side lobes extending in both directions. And similarly here you have the main lobe and side lobes. Okay? This is what we expect to see just by using basic shifting theorem. Okay, shifting theorem modulation. Okay, this is what we expect to see. So instead of seeing spikes, we see a main lobe, which has a finite width. Okay, which has a width, and you know that the width is inversely proportional to the duration of that window. Okay, this is what you expect to see. Okay, so as a summary, so in the time domain, we multiply our signal with a window, and then when we quickly go to the frequency domain, because we have two tones, we expect to see one component around omega 1, another component around omega 2. Okay? So this is what we end up seeing. Okay? This is what we end up seeing. Exactly this Fourier transform, after we window the signal, and the signal has two tones, we expect to see a main lobe, pretty tall, a tall main lobe. But if you look closely, there are side lobes. These are the side lobes. That's around right here, around that right there. Yeah. We expect to also see some side lobes. But otherwise, the main lobe, we see two big components. One big one located at omega 1, which is, if you convert the frequency axis back to hertz, oh, this must be around 700 something, right? You can tell. You can see a big main lobe right there. Another big main lobe right there near the intended frequency. Okay, so in the frequency domain, we will be able to estimate the tone frequencies by looking at the location of where we have peaks. Looking at the location of peaks, spectral peaks. And this is the process what we call spectral estimation. We're estimating some kind of property of our signal in the frequency domain. So that's why we call it spectral estimation. 频谱上面的一种估计，一种估计。All right, so I believe in the homework, in the starter code I gave you, there is, but this is just not yet short-time Fourier transform. This is one frame, one spectrum. Okay, in short-time Fourier transform, remember that big X, omega, n, m, is defined as summation. Now let's say the index is still n. Xn. So I remember in the last lecture I suggest that we shift our time, our signal to the left by m samples. Okay? And then we fix the location of the window and then take the short-time Fourier transform. That's what's meant to perform a short-time Fourier transform. Shifting our signal to the left by m samples while taking the Fourier transform of the window signal. So that's why the result is not both a function of omega, it's a time-varying spectrum that we're going to be seeing. So I remember that in the homework I gave to you, if it's already started, there is a 3D plot that I made. There's 3D plot, and then in this axis we get the frequency, in that we get f, and also I'm showing to you the magnitude response, the magnitude of x omega m. Okay, so check it out. So check it out. So we have a plot like that, and you're free to drag the 3D plot in MATLAB and see the short-time Fourier transform, the spectrogram, from different angles. Okay, I hope that is helping you to now turn this into a 3D representation. Have you started? Homework number 5? Okay, so we have used the kind of shift theorem. We're multiplying our W is being carried by our tone. So consequently, the spectrum is a simple shift in the frequency domain. Okay. So I think this should be pretty clear. So now, the issue of window, the issue of choosing the window. Okay. So if you agree with me that indeed we expect to see main lobe and side lobe, so then your choice of window would make the result look different. Okay. Not only here, but also in your homework number 5. In part of the homework number 5, I asked you to try to change the type of window. If we just fix it, for example, on this page, when we fix the window length to be 20 milliseconds, but we can choose in between rectangular window and hung window, the results will look different. Okay? The result still, you are going to see the two tones, two peaks right there, but the side lobes are much more prominent. 更明显了. The side lobes, when you use rectangular window, the side lobes are much higher, much larger, much higher, much more prominent, 更明显, much more obvious than using hung window. Yeah, can we agree on that? Did you notice? Right? And what else? What's the other difference? Is there something else is also different? How about the width of the main lobe? So again, we see over and over. Before we were using window for filter design, but this is another context where windows are used. Okay, in the entire semester, we talk about using windows for designing FIR filters. That's a totally different topic. Here we're talking about spectral estimation, but also because of the nature of trying to visualize something on the time frequency plane, you got to choose your window. And depending on your choice, rectangular window has a narrower main lobe, which means the spectral resolution is higher. Okay, narrower main lobe. The main lobe is not fat. It's the narrowest. Okay, but then the side lobes are more prominent. Okay, side lobes are more prominent. 比较明显. Side lobes can be much higher than if you use hung window. Okay, and similarly, you can just replace the hung window further with a Blackman window. What do we expect? When we use the Blackman window, also 20 milliseconds, do we expect to see the main lobe, even wider main lobe or anything? Okay, do we expect the side lobe to be further suppressed, even better, smaller than that? Okay, so that's kind of now it's a question that can be you can discuss, right? You can discuss that. Choice of window matters. It affects two things. One is the main lobe width, and the other is the side lobe height. Okay, the height of the side lobe, the width of the main lobe. And here I do have a few comments. So in spectral estimation, if the goal is to identify all sinusoidal components, so there's a subtle difference. Let me try to explain. There are two different kinds of tasks. Okay, in one kind of task, like for example in today's task, if we know a priori, if we know beforehand, okay, a priori just fancy word, Latin word for beforehand. 如果我们事先a priori, yeah, you should have told me a priori. 你应该不早告诉我. You want to be really fancy. Tell somebody to tell you next time. Tell me earlier rather than. If you don't know, if we know a priori, we know beforehand in advance that there are going to be two tones. Such like we are on the telephone system, right? We can very safely assume either a button is pressed or a button is released. Can you simultaneously press two buttons? Can you do that? Have you tried that as a child? 小时候有没有尝试想要同时按两个电话号按钮 ？Anybody？ 有没有这么白目，这么中二 I think they designed it so you cannot. I'm sorry. I'm pretty sure you cannot press the two tones at the same time. Okay, but so we know if we know a priori there are at most two tones or there's no tone, right? It's fine. So if there are at least at most two tones, then actually I would recommend using rectangular window. Why? Because it has the best resolution. You look at the main lobe; it's very nice, very narrow. Okay. We know a priori that we are looking for two tones in the spectrum. Which two tones are? They must be this one, the biggest one, and the biggest one, right? Must be them, nothing else. We know a priori that they are at most two tones, okay? So we know that, oh, there are two tones, one at this frequency, the other at the other frequency, okay? Everything's easy. So that's our task. Our task is a simpler task. We can, by assumption, assume that we know beforehand there are at most two tones, okay? But imagine this. Well, how about if there is a more difficult task where the number of tones is unknown? 如果没有事先知道有几个 pure tone 的话，that's more tricky. The task becomes trickier. Why? Let's say if you apply short-time Fourier transform, and when you go to a frequency domain for any single at one moment, you look at the short-time Fourier transform, it looks like that, the magnitude, okay? Can you safely tell me that there are only two tones? Can you be sure? Are you sure there are only two tones? Simply by looking at the frequency domain result. Can we just be so confident that there are only two tones and nothing more? What if somebody tell you that, oh, okay, I took a look, and there's a big tone right here, another big tone right here, plus a sequence of smaller tones right there. Yeah, right there. Are they wrong? Are you? Yeah. How can we tell if that's wrong? You see, yeah. When we do not know beforehand there are two tones, then this becomes trickier. Yeah. Then there's no simple way for you to tell. Oh no, sorry, there's a peak, but it does not correspond to a tone. It's just a side lobe of this main lobe. Then you need some extra effort to examine that. Okay? To exclude the possibility that there really is a smaller tone at how many dB? 4 dB, I don't know. If you're seeing a big tone at 24 dB of magnitude, oh no, not 24 dB, but 24, right? Linear scale right here. You can hardly be sure that there isn't a tone at this magnitude, whose frequency is close to 770 but higher. Let's say 790. Okay, I don't know, right? So you cannot be sure. So it's pretty confusing. Okay, it could be pretty confusing. So imagine that instead of analyzing telephone buttons, you're analyzing a piece of music, real music. Let's say you plug your guitar string. The string's making sound. There are going to be a known number of tones because of this guitar. Okay. Then it becomes hard for music transcription. 要采谱就没有那么简单嘛 for music transcription. Okay, so you need to kind of think twice before adopting the rectangular window. So in that case, I do not recommend using rectangular window because of the trouble that the high side lobes are giving to us. There is going to be trouble. Okay, when we try to interpret what's inside this spectrum. Is that making sense? Without knowing, we do not know in advance that there are two tones only. Okay? So in that case, I recommend not using rectangular window. Okay? Maybe using a Hahn window. And you know that, let me go back a few slides. Using Hahn window, even though the main lobe now becomes wider, we said the spectrum is smeared a little bit, 有变抹到两边去。But the splattering， 这是有名字的啊，这些都有名字。 To widen the main lobe means the verb to smear. Smearing versus splattering. Sometimes in the field of audio, people talk about smearing, spectral smearing, spectral splattering. 这两个字蛮有意思的啊。Smearing, splattering. Smearing means to widen the main lobe in this context. Splattering meaning that we have another side lobe that goes that's outside the main lobe region. Smearing versus splattering. So that's a choice of window. What I'm talking about. Okay. So anyway, so the choice is up to you, right? It's just choice of you. If you want to ensure that there's no splattering, then choose high. But if you want to just maximize the resolution or to make the main lobe most narrow, then you use the rectangular window. Okay, so that's kind of the guideline for choosing the window. So far so good. I think I'll just continue talking. Okay, so a question for you. Now question time. Smearing, splattering. 英语教学时间。What does these words mean? Smearing 造句。有人会用 smear 造句吗 ？Smear 跟 splatter. You can also, check. Let's take a break and please check what's the meaning of smearing versus splattering and tell me. Make a sentence. Find a sentence. Smearing or splattering. What does that mean? 这有点帮助我们了解了啊。为什么？其实我觉得我们在学科技那个英文还是蛮重要的，因为很多的名词它会取得比较活灵活现的。如果用英文来去理解那个名词取得，其实有时候蛮有趣的，是很活泼的。科技英文是可以很活泼，通常我们觉得科技中文会比较严肃一点。好像你讲所有东西都很严肃，但英文有时候它原用语是相当的活泼的啊。Okay, maybe I was just saying that sometimes these jargons in English they have pretty vivid meanings. Okay, it's not at all, not at all. So it's not always so serious the way they name things. Splattering. What does it mean to splatter? It's a verb. Splattering. Anybody splattering 什么意思？什么意思 ？Splattering 什么意思？飞溅。飞溅哪一个溅？水字旁。It's like imagine there's a pot of water and it's been raining these days, right? If you just intentionally step on the water and to make the water splatter, to scatter the water all around you. That's what it means to splatter. 那这个撞声字啊，I don't know the term. Splash, splatter, 这一类的都是这种切开啊、分开啊、那个这种意思啊。To split, right? 所以这类的 SPL splattering. Okay, spectral splattering. Imagine that now the energy is scattered around away from its actual. That's a spectral phase. This is a fancy way to refer to the side lobes. Okay, a fancy way. This is a fancy term. How about smearing? Smearing anybody? What do you mean to smear? 磨过去，橡皮擦 ，smearing， 橡皮擦磨过什么呢？磨过表面啊，是。颜料啊，对，画油画。对，那这个是只是在溅开来啊。对 ，smearing is more like anybody smear. Have you been smearing something in your life? How about peanut butter, right? Take the knife and spread. Smearing is more like spreading. Spreading like peanut butter on a piece of bread. 花生酱那种感觉，这样子抹它啊。So this is like smearing. So delta function is before smearing, after smearing, now is somewhere there 啊。想象一下啊，涂面包啊，应该那个番茄酱不是，然后要把它涂满整个表面啊。Smearing versus splattering, fancier way to refer to main lobe versus side lobe. Okay, two verbs. Okay, maybe we can take a break. Let's take a break. 哎，回来了啊。 So yeah, we need to make sure what materials will be covered for the final exam. OK，期末考的范围哈，好，我们这个今天就早点再继续开早啊。那先一些，不过你要是啊，
就用我们调 Windows Lens 调，是这个吗？
这个是用。Okay, so let's come back to the link. So before we resume, let me make a few corrections. So I just because I was late an hour ago, so I lied my TAs to make the announcement that today's material will not be covered in the final exam. 今天的 lecture 的部分啊。So today's lecture, the entire lecture 11, will not be included in the final exam. But homework 5. The written part, there's a PM algorithm, right? So we spend so much time talking about the PM algorithm. So that will still be included. That's still in the range of the final exam. But otherwise, the final exam will be from the end of the midterm to lecture 10. Is that fair? Is that clear enough? End of midterm till lecture. Wait. 应该说对 end of the midterm 的范围啦啊。Whatever that's not covered in the midterm will be considered in the final exam. And that is to say, you don't need to spend a lot of effort to review like chapter 4. Chapter 4 has already been covered in the midterm. But that being said, you cannot completely ignore basic concepts such as sampling, right? Aliasing, sampling, because it's 这些的东西都有累积嘛 right? What you learn has been accumulated, right? So it's hard for me to promise that that nothing in chapter 4 will appear. I will not promise that. But I don't recommend study so hard for chapter 4. Try to focus on chapter 5 and chapter 7, maybe a bit of DFT and FFT. Right, okay, and in tomorrow's discussion, I believe I created a set of 6 questions, right? Is it 6 or 5? 6题还是5题？明天要讨论6题 right? So in one of those 6 questions include DFT or FFT, right? So you know sort of the weight of the final exam. 可能重点还是会在第7章最多了。In chapter 7, we learned so much. We learned IIR design. Butterworth, right? We learned FIR design, a few different methods, right? So please focus on, try to emphasize, put more effort in chapter 7. 这样子，关于期末的范围了解吗？可以吗？有没有其他的建议？或是不清楚的地方 ？Everything clear? Everything clear? Yeah. Okay, so let's come back to this slide. The PowerPoint right here is showing my comments on the choice of your window. So I suggest choosing rectangular window will be fine if you know beforehand the number of the tones in the spectrum. Okay, but if you don't, I suggest to play safe, maybe choose another window, maybe a Han window would be a good sort of trade-off in between smearing and splattering. Its main lobe is not too wide. The side lobes are all at least 40 dB down there. So it's not bad. Not a bad choice. So further, the next slide is still on the same topic, just resolution. Now the concern is resolution. Have you ever wondered, now you know the system, the telephone system, each button has 2 tones. Okay? Now you know that. Have you ever wondered, now do you wonder, can I press the button so short? like so short, so that the system cannot recognize two tones. Is it possible? Is it biologically possible to move your hand so fast? Right? What's the quickest, the world record for dialing a sequence of 10 numbers? or 这很重要 ，right？ 你知道那个玩俄罗斯方块，就这几年前有人说全破300关，有人 follow 到这则新闻呢 ？Tetris 有 follow 到啊，在座有没有玩家？我就好奇说300关是怎么回事？就是他们是发明了一种可以按超快的方法，有些人还用脚，还是有看过那影片？就是 seriously, this is a signal processing problem. Okay? How fast is too fast? Can you ever press a telephone button so fast that system would not be able to recognize the number anymore? Is it possible? So let's kind of analyze this. So this is, again, number 5, which is a combination of 770 and 1336. Fine. So using a 20 millisecond window, you see very nice separation of the two tones in the frequency domain. That's good. But let's say, imagine if your pressing is around 2 milliseconds. Let's say 3 milliseconds. If you can press it and release in 3 milliseconds, complete that, which I don't think is possible. In 3 milliseconds, it's a pretty short time. And then the system now needs an even shorter window, right? You press it only 3 milliseconds, the window got to be even shorter, right? So let's assume that the window length is 2 milliseconds, and then this is what we're seeing. Then you see that now, really serious is it smearing or splattering, or both. Yeah, you see where the problem is? Big smearing. 2 millisecond window, rectangular window, that's a side lobe. The side lobe and all of them are very wide, okay? And you can verify, 2 milliseconds correspond to 1 divided by how much? 1 second divided by 500, right? 500分之1秒啊。So that means the main lobe width is 1,000 hertz. Just simple matter of fact. Yeah? Simple matter of fact. Or this is not even rectangular. Are we talking about rectangular? Or this is a rectangular window. The main lobe width, I was 是，怎么会只有这么短？我会以为是 Yeah, I was expecting. So anyway, it's roughly inversely proportional. Okay, the main lobe width is inversely proportional to the duration. Right. So now you see big chunk of main lobe, as well as the side lobe. And now now when you look at this spectrum, okay. Can you still estimate that there are two tones? One at 770, the other at 1336, and successfully decode the number, which is 5. You see, maybe or maybe not, right? It's not as easy as this scenario. Okay? When somebody presses a tone and release it in 3 milliseconds, then it's pretty challenging. I say maybe the system can still handle that, but what if you press a tone and release it in 1 millisecond, right? Then you are a machine. 那就说你就不是人类。Right, that's a very simple way to tell a machine from a real person. Yeah. Okay, so is it ever possible to press a tone too fast, right? Yeah. So the rule of thumb is that the resolution is about smearing, okay? You want the smearing to be limited. You want to limit the smearing. Therefore, delta F, the width of that smearing, the main lobe width, you want it to be narrow. And we know that the main lobe width is inversely proportional to the duration of the window. Okay. So therefore, let me just read it first. Since the main lobe width of a window is inversely proportional to the duration of a window in time, and we need to use a sufficiently long window to resolve two spectral components. Okay? So here's an example. If F1 is, in our example, 770, F2 is 1336, Then delta f, the frequency separation, we have a separation of 566 hertz. So that means if you take the inverse, 1 divided by that equals to 1.8 millisecond. So the tone, the button needs to be held there, to be holding on there, at least 1.8 millisecond for the two tones to resolve in the frequency domain, for the two spectral peaks to resolve in the frequency domain. Otherwise, your resolution is not high enough. So resolution here is we are sort of borrowing a terminology from optics. 光学啊，光学讲解析度，对不对啊？What's the smallest angle you can tell from 解析度啊 pixels 啊。And here we use the same terminology, resolution. If you have two tones that are separated by this much, then in the time domain, you want to last for more than that in order to resolve the spectral components in the frequency domain. That's a simple consequence of smearing, spectral smearing and spattering. At least that. The longer, the safer. Okay. So now, if I ask you, now consider the entire touch panel. Okay. Now consider the entire telephone panel. Can you say how fast is too fast? Can we answer this? Now, my original question, can you ever press a button so fast that the system failed to recognize the tones? Is it possible? Now, looking at all the possible combinations, we have 16 buttons. We have 16 buttons, and the closest separation, which button has the closest separation in the frequency domain? Which button? 哪边？左下角星星对，星号米字号啊，米字号。This guy has a separation between 941 and about 1200. Okay, then you can calculate. How to press it too fast. And try it at home. Okay, it's probably biologically impossible. Okay, so this is well designed. Very well designed. Okay, so now let me just briefly mention this. This is really totally more advanced than what's typically covered in DSP. Resolution versus another term I promised to explain, accuracy. 解析度跟准确度 slightly they have different notions. 意思不太一样. So now, the way I define accuracy is a concern when your observation is subject to noise. When you take a measurement of any signal, there's always noise. In speech or in biological signals, in everything, there is noise. So for example, if you take a look of this trace, this orange trace, which has a lot of fluctuations, right? That's signal plus noise. I made this plot by adding on top of adding a noise sequence on top of my signal. So when I sum the signal and the noise, the result, one instance of the result is like that. 我讲是有一个 instance 一个范例因为 noise is random, right? So each time is different. It's stochastic. So this is just one instance of a noise subject to some kind of statistical property. 有些统计特性Signal plus noise. That's what's being encountered all the time. So now the question is, can you now be sure that they're underlying the noisy observation? This is noisy observation. Can you be sure they're underlying there is this one pure tone? Can you be sure? Or it's a combination of several tones? So you see that now it becomes tricky, right? This is for the case of one tone. Maybe you can just by 把就可以看一看by 其实把就可以是一个叫什么noise removal Yeah, you may be able to say, hey, I see a pattern. I see repeating pattern, right? I see repeating pattern, things going up and down, roughly periodically. 大约是周期性. Okay, so there got to be one component beneath, one periodic component beneath this noisy observation, right? Now, and chances are you may be right. Okay, so now, but how about this? Now, can you safely say that this is two-tone combination plus noise? It's not smooth anymore. Okay, it's going up and down in a not so smooth way, right? Signal plus noise. So now, quickly, let's hear it, but I need to make sure the volume is not too loud. Okay, let me turn down the volume. This is what it sounds like when we press button number 5, but now somehow the network has noise. Okay. Okay, let me just soften the volume and then try to play it. Yeah, so that's what this sounds like. Okay, signal plus noise. Now, when you design a decoder, are you confident that you can decode this number, right? Whenever there's noise, there's noise. So now, noise, apparently it affects the accuracy of estimation. And I claim that even if the resolution is good enough, okay, even if you use a long window, even if this pressing lasts for long enough, 1 entire second, so you have time to decode, the resolution is not going to be bad. But the noise might affect the accuracy. So let me explain. So this is in the time domain. So immediately when we go to the frequency domain, this is what happened. Now this is the spectrum. Again, using the Hahn window of length 20 milliseconds. Okay? So what do we see? What do we see? We see arguably two tones that have unequal height. So now that the height, even the heights become unequal. And the 高度变不一样, right? And what's more? What's more? You see? Like under here, you have some random peaks. Random peaks. They just randomly show up. Okay? And this is exactly a very simple example you can easily simulate. Okay? When you hear a sound like that, number 5 with noise, and this, and then you go to frequency domain, hoping to extract two components, can you do that? Can you still estimate that this is number 5, not 4, not 6? Can you still do that? Can you still do that? Is this still 770 hertz? Is this peak located at the very top of 770? Is this very top, this apex, 这个顶点, or is it the apex exactly 770? Then maybe not necessarily. Maybe accompanying with all the contamination, 这些的污染啊，我有时候用这个字 contamination. Accompanying with all contamination right there in the noise floor, the peak is more or less shifted randomly. Maybe you will underestimate the frequency, maybe you will overestimate the frequency because of the noise. Okay, that's an important concept I want to share. Okay, so my voice is not going to be affected. contamination. All right. I want to improve the signal-to-noise ratio by closing the window. Okay. So you see that there's noise, and there are random peaks, and also the height as well as the location, I argue, will be affected. You can no longer estimate the frequency, actually, as well as the amplitude, in the most accurate fashion. Okay? So turns out that in the next few slides I'm going to introduce to you, just quickly go through with you that there's a mathematical foundation for analyzing the influence of noise. Okay? In any estimation, if you can just formulate the question as of parameter estimation, and then if your observation is under noise, and there's some theoretic bound. And this is an advanced topic. I just want to share with you. So if you're further interested, you can maybe take another course, information theory and estimation detection. Right? Anyway, so I'm saying that this is to compare before and after adding noise. Okay, Hahn window, 20 milliseconds before noise, after noise. So they look really different. Okay. So a bit of summary, resolution is a concern against interference from concurrent sinusoidal components. But accuracy is concerned against noise. Okay? And resolution, we mentioned that to separate two tones, you need at least the amount of time that is inversely proportional to the separation. That's a relation for resolution. For choosing a sufficiently long window, use this. But accuracy, turns out, accuracy has a different relation. Let me just mention this without proving, okay? Accuracy, whenever there's noise, let's say your noise is white noise, Gaussian white noise with variance sigma square, okay? Right? And A is the amplitude of your signal in the time domain, okay? A cosine theta, right? A cosine omega t. So this term, sigma squared divided by A squared, that's the inverse, the 导数, that's 1 divided by signal-to-noise ratio, right? That's the noise power, that's the signal power. There's a factor of 2, not that important. So sigma squared divided by A squared, that's like inversely proportional to the signal-to-noise ratio. But otherwise, the accuracy is going to be affected by, but you can still try to just use a longer window, still helps. But now the relation is not inversely that of the inverse proportion, but the cube of your accuracy is going to be inversely proportional, no, not a cube, the square. The square of your accuracy, okay? The smaller the better, okay? Smaller better. The square of the variance of your estimation error, so to speak, okay? If you do everything the best you can, then that performance is going to be inversely proportional to the length of the duration of your window. And that's a somewhat less known property. This is not well known. Okay? This one is much easier to understand, but this one is not so well known. It's a relation between the square of estimation error versus the length of the cube of the length of your window. So the theoretic foundation for this, okay, and here you know that A squared divided by sigma squared is a signal-to-noise ratio, right? The foundation, if you search for a keyword, the keyword you want to search, you want to ask your AI, is called Fisher information and Cramer-Rao bound. Okay, just for your reference, Fisher information and Cramer-Rao bound. And then I'll just quickly go through Fisher information and Cramer-Rao bound in 10 minutes. All right. So now the mathematical notation. Suppose that your signal S is subject to contamination by noise, but otherwise both of them is a vector in the n-dimensional space. Okay, n being the number of samples. And the result, your observation is X. Okay. So the formulation goes this way. Suppose that your signal is parameterized. What does that mean? So suppose, for example, our signal has a frequency, unknown. So frequency is a parameter which we want to estimate. Then we say the signal is parameterized by the frequency, which is unknown, okay? So let's say theta in general is a parameter that is unknown, and which we want to estimate, so that S is equal to S as a function of theta. And then we also assume that U follows some sort of distribution, and this is its PDF. It's probability density function. Okay? Suppose that the probability density is given. Then now, X becomes also randomized, right? Because of the noise. Now X, your observation is also random. This part is deterministic, this part is random. 这已经决定了啊。这边没有 noise， 这边有 noise. Okay, this part is without noise. Your assumption, you assume that it's parameterized. You believe it's generated in a certain fashion, such as by pressing down a button on telephone. So, under some assumption, you can safely, confidently say that S is parameterized. Now S is subject to noise, of which the probability density function is known. It's given to you. So as a result, X is also following a distribution. Okay. Now F is X, the PDF for X. That's our notation. X has this PDF, which is parameterized. PDF is a function over the n-dimensional space. But now that distribution is parameterized. That's the way we formulate this problem. Okay? So if you bear with me for now, question is then, how do we best estimate theta by looking at X? Okay? Each time you are given an instance of X, such as a sequence of your signal, a finite length signal, right? N-dimensional, random, there's noise in it. So now, in terms of the flow diagram, okay, parameter estimation block diagram can go this way. Let's say theta determines S, which is being observed, but the observation is subject to some contamination by random noise with known statistics. So now, basically, this is a fancy way to say X equals to S plus U. Now, by observing X, by taking a look at X, you want to construct an estimator which gives you an estimate. Again, theta hat is a notation for estimation. Okay? By looking at X, we construct an estimator, a decoder, that tells you, oh, my best idea about what theta is theta hat. My estimate of this unknown parameter is denoted as theta hat, which should be a function of X. Okay? So that's a very general formulation. We're not even doing any calculation yet. This is just about setting up the stage. Right? 只是把这个整个 framework 建构起来而已。Beautiful formulation. So this is kind of my own intuition. So what's going on? Now, in the most simple case, when your S is parameterized by only one variable, theta, then depending on when we vary theta, the set of all possible S will form a trajectory, a path, a curve. Right? When we vary theta, then S, all the possible S will form a curve in the high-dimensional space. Okay? So imagine that in an n-dimensional space, you have a curve. All the possible clean signal should be along the curve in this high-dimensional space. Okay? Can you imagine that? But now the problem is any signal is going to be contaminated by cloud, by an uncertainty caused by the random noise. Okay? So instead of directly observing one point exactly on the path, you see a point, given that the theta is this, your observation can possibly be anywhere around there, due to the presence of the noise. And that's the way we formulate the problem. Okay, so now by taking a look of your observed signal, which might be not exactly, with probability 1 is not be going to be on the path. It's somewhere here, somewhere there, over there, around it, but not exactly on the path, not exactly on this curve. So how do we estimate? What's our best effort to estimate theta? What's the most likely choice given your observation? Okay, so this is the way they formulate such kind of problems in communication. In communication, so pressing, decoding a button is communication problem, right? So that's a kind of very, very general formulation for any sort of communication, for this particular sort of communication, parameter estimation. So here, that's what is meant by when we say X follows a distribution, but that distribution is parameterized. Okay? Depending on where theta is, this cloud, this yellow ball can move. You imagine a yellow ball moving around along the path. That's what we mean a PDF, a distribution which is a distribution over the n-dimensional space which is parameterized. That's the way we formulate the problem. Okay? Is it making sense? When we say a distribution over n-dimensional space which is parameterized by a single variable theta. Okay? Nice, very nice choice of variables. So now our task of constructing an estimator becomes to find theta such that the observation X is optimally explained. Which theta best explain your observation? That becomes the way we look at it. You're given a piece of signal. Now, which telephone button best explains our observation? Okay? So it turns out there's a theoretic bound. Okay, there's this piece of function that's defined as taking the log of that and take the partial derivative and call it v, and then the expected value of v squared is called j. For those that are interested, please talk to Professor Hong Yuewen, Zhao Qicao, Wang Yonglu. Anybody from Tongxin Suo, they will be sure to explain it to you. Okay. And turns out this j thing here is going to be parameterized. Okay, j is a function of theta. It's called Fisher information. And now here finally comes the theorem. Okay, and there's a reference I think I can point out. I have this book on my shelf. Which I'm not going to give to you. It's a very precious book by a professor I respect a lot, Tom Cover. Cover is his last name, Tom Cover. So it turns out that when we define j theta as the expected value of this first part of the square of the first partial derivative of log of the distribution, okay? Turns out that then there's a theorem. If your estimator is unbiased, okay? Let's say you estimate theta, you construct an estimator, right? And depending on X, the result may be different, right? But however you get the result, the expected value there is always equal to theta itself. If this can be guaranteed, we say the estimator is unbiased, okay? Then we have a very important property that I'm just going to tell you, to refer to you. We're not going to prove it. And it turned out that then this is the variance of your estimated error. Okay? The mean of your estimation is right on. Okay? If the mean of your estimation is right on, but there's uncertainty. Okay? So how about the variance? The variance, that's the variance of your estimation error is guaranteed. It's never going to be, it's lower bounded by 1 over j. That's a very beautiful, well-known theorem in detection and estimation theory. Okay? I just want to refer to you, what is J? J is called Fisher information. It's a really advanced topic. This is蛮advanced. Okay? Usually when we talk about information, we talk about Shannon's entropy. That's what you typically learn from your first course in information theory. But Fisher information is another topic, okay? Another kind of information, how we measure information. J measures the amount of information you have. And it's, the relation goes that if for any unbiased estimator, the variance of estimation error is lower bounded by 1 over J. And that 1 over J thing is called Cramer-Rao bound, okay, CRB, Cramer-Rao bound, which I mentioned. And here's an example. For example, we will finish our lecture after we talk. I finish this. For example, if we have a signal model, we are sure that our signal is parameterized by one unknown frequency. That is a frequency, parameterized by omega. Okay? I'll assume that for now, assume that we know phi and a, right? But omega, the frequency, is unknown. And then we are taking an observation of a block of n samples. So x now becomes a vector in the high-dimensional space, a column vector. And u is subject to Gaussian normal noise. The distribution is Gaussian normal and IID. Very much simplified scenario. And then you just apply the formula. Okay, log of f takes the e expected value of the first derivative, partial derivative against log f, against omega and so on. And J, that's the Fisher information. J equals to signal to noise ratio times a third order polynomial of n. What is n? N is the length of your observation. A third order. So roughly speaking, therefore, the estimation error is lower bounded by 1 over J, which is called CRB, the Cramer-Rao bound. Okay, you don't want to memorize the name. 1 over J, which now, according to this sort of derivation, you get the result of sigma squared divided by a squared divided by just some kind of polynomial order, third order to a third order. You can follow step by step. And if you are patient enough, you may be able to obtain the same result. And this, again, is commemorating 51-year anniversary. This has been discovered 51 years ago. 51 years ago. IEEE transaction of information theory. If you will, take a look, right? So that will be it. Okay, so why do I give this lecture? Apparently, we cannot test you on this. Okay, just want to encourage you. 学海无涯啊，学海无涯，对不对？回头是岸，不是？There are always new things to learn. Always things so many new things to learn. Learning makes us humbles ourselves. Okay, so be humble and just stay foolish, stay hungry. Right. But with that, thank you for being here, especially for today. I apologize for being late, and that will be the end of all my lectures. See you tomorrow for the discussion. Thank you.